Good evening. My name is Yasunori Yamamoto from Life Science Data in Japan. So I'm talking about this title here on behalf of the first author of this paper, is Daniel. He is now busy and also in Spain now, and also he is now online. So if you have any question, you can talk directly to him. Okay, let's start. Okay, first, I'm briefly introduce the RDF shape. So maybe I think all of you already know that, but maybe to briefly introduce. So RDF shapes are frameworks that are for describing and validating RDF content. So this is the example here. So RDF shape is for RDF dataset. It's kind of specific for subject. So for each subject has to specify this kind of properties. So this is a label, and there's an open parenthesis here, and here it's a for specifications for properties, and for each property there's a kind of a specification for here. So for example, this is a user must have a name here, and could have a birth date here, because this is a question mark. So question mark means a 0 or 1 property or object for this property. And also their gender must be schema male, schema female, or different value expressed in the string here, this one. And also could know other users. So this is at mark here. So at mark means the other label for shape. So this is kind of in reference for another shapes. Okay, this is an example here. So if we apply the shape into this RDF dataset, what is the result of the validation here? So for these 3 subjects, for each subject, this shape can be applied. So for this one, it's valid, and for this one, it's also valid. But the third one is invalid, because you can see this one. So the property object is only an integer, but the shape says the birth date should be XD data type. So XD data type, date type is not an integer. So this is invalid. So we can use that kind of stuff for validating RDF dataset. Okay. And so here's an example in the life science domain. So this is a database called glycoepitope. So do you know any one of you epitope? I'm not sure because I'm not a specialist for glycoepitope, but just for briefly introduce this epitope, what the epitope is here. So epitope is kind of part of antigen, and the antigen is part of antigen is recognized by antibody. So this is a kind of a big, like bean shape is an antigen, and part of the antigen can be epitopes. So each epitope has its own shape, and epitope can be recognized by antibody. So this is very important for immune systems. Okay, just for brief introduction. So this is a database of epitope here, and this is one page for epitope. And this database also reduced in the RDF dataset. So this page can be represented in this RDF data. And this RDF data is also recognized by this shape. Okay, so by you seeing or checking this shape, the user can see or learn what the database look like the kind of a structure of database you can see from this shape. So okay, very useful. So the RDF shapes ensure that an RDF dataset is consistent and reliable, and also crucial for data integration, sharing, and interoperability across different systems and applications. So it's very useful. But the creating this and maintaining RDF shapes can be very challenging because there are many kinds of shapes. So if you have any database for complex, so each for the RDF shape is applied for each subject type. So if you have many kinds of data set, you have many of RDF shapes. So it's very complicated to develop a shape from scratch. And so there are also in the life science domain, there are many two many triples in each dataset. Like so, for example, UniProt has more than 148 billion triples, and also Wikidata has more than 15 billion triples. So it's very difficult to maintain, and also those kind of stuff is updated periodically. So it also shape also have to be keep updated with this kind of stuff. So it's a challenging stuff. So that's where the shape extractors come in here. So shape extractors are for obtaining shapes automatically. So these shapes could be used for describing data and also validating data. So one example of implementation is RDF extractors, SHECL. SHECL is developed by the first author of this paper, Daniel. And the SHECL can get access to RDF dataset and automatically generate a SHECL schema for describing the RDF dataset given by input. Okay, so, and this is one example for using the SHECL in life science domain. So usually we develop RDF dataset by using a computer program, and also it converts from existing other non-RDF datasets such as CSV or MySQL or other stuff, and not an RDF dataset. And from that data, we usually develop a program to convert from non-RDF dataset to the RDF dataset. So by using this one, so SHECL can produce or generate these kind of SHECs from the RDF dataset. So by using this SHECL, the RDF data developer can check what the dataset look like, and they can check whether the resultant database is expected or unexpected. So not only getting this kind of shape, the SHECL can also produce this kind of statistical data here. So if you see this kind of statistical data, you can check, oh, this is an outlier, or this is an unintended or unintended one. So by checking this kind of stuff, you can modify or edit your program to generate a RDF dataset. So that SHECL is very useful, this kind of stuff, for maintaining or developing a RDF dataset. Yes, but even though the SHECL is very useful, it has also issues, because most extractors like SHECL has scalability issues when handling large inputs. So as I said before, the UniProt has more than 148 billion triples. So if we put that data into a SHECL has a memory out-of-memory error. So we have to think about another way to get RDF shape from a huge amount of RDF datasets. So existing approach is sampling. So I show you some sampling approach here. The sampling approach is kind of literally, it's just a sample from the dataset. So there's a huge dataset here, and you can sample of some RDF data from here to small subset. And then for this subset, we can extract a shape expression from this data. This is a usual way of sampling approach. But this approach also has an issue or drawbacks, because sampling approach may introduce bias in the shape due to rarely observed features. So if we get sampled properly, it's good for extracting a good shape, but the frequency of the RDF data set or some shapes can be dropped because the sample drops some of the RDF data set. So it's kind of drawbacks. So our proposal is a slicing and a consolidation approach. So first, we try to slice or split the RDF dataset into several kinds of slices. And then for each slice, we can get or extract a shape from each slice. And after getting the many slices or shapes, we can consolidate into one shape. By using this approach, we try to represent or make more reliable shape from this one huge RDF dataset. Okay. So the basic approach. So how to slice? So this is the first step. So this is very basic approach we took. So simple experimental slicing approach, first using n consecutive triple from the original source. So this approach also could introduce a bias too, because even though we slice the whole entire RDF dataset, there's kind of drawbacks here, like here. So one example here, this is a successful slices. This, for example, here the RDF dataset, and from here it's split and slices are different RDF dataset. So, but for this dataset, we can sufficiently get the shapes for this subject. So it's a successful example. But if the split happened from between these triples, so we only get this type of shape, and this part of the RDF data cannot be accepted for this RDF shape, because so RDF extractor or shape extractor only for getting focusing on this RDF type triples. So this part, there's no RDF triples here, so we can't get any shape from this part. So this is kind of a drawback for our approach. But we assume this happened not on this is happened only for tiny part of the whole dataset, because the dataset is a kind of billion triples, and this happened only for the number of slices. So it's very tiny and marginal, I think. So we took this approach here. So how to consolidate? So this is a bit busy slide, but this is a center or core of our approach. So I talk this one steps here. The steps to consolidate two shapes schema S and S prime in the resulting schema R as follows. So we look for the shapes whose level is just in one of the schema. Those shapes are directly included in R. So this means that so there are many shape slices, and if only shape are in one slice, it could be no problem. So we don't need any consolidation for that shape. So this is the kind of stuff we say here. And for the rest shapes, the pair and S and prime S having the same level, we create an empty shape R, and this is 3 steps to get that consolidation. So here, this is a kind of graphic image of the consolidation. So first, the split into slices and get shapes. And so for each file, there are several shapes. And if we get kind of shape 1 only from here, this file, we don't need any consolidation. So this shape into this part. But for this shape, shape 3 is also in this shape file and also here. So we need consolidation to be merged into one shape. So this is kind of depending on the shape, we have to take a special approach for this consolidation. So this is an example here. So if we have this one and this one in 2 slices, and we need to consolidate from these 2 slices into one shape, we do 2 steps here. One here. So this part is both in this shape and this shape, but it's only identical, so it's no need to do some special care. So just from part of into the resultant shape here. But for this part, so this shape hasn't this kind of shape here, so we have to take special care for these shapes, because so this slice, we don't know this is a complete shape or not. Like if we get kind of a split shape from here, we have to take care about that kind of problem I said before. So here, this is just one no notation like a plus or question mark, but this shape doesn't have any constraint for this part, so we have to take care of the question mark here. And also, this is a plus mark, but also this constraint doesn't here included here, so we have to change to the asterisk here, like that. So we have to take that kind of consolidation. And also for this part is already get a question mark, and this is also doesn't have any constraint here, so we don't need any care, just copy from this constraint into the resultant shape expression. So this is our basic approach for consolidating the shape. And so prototype we developed, and we can you can get this source code from here. And also this is experiments. So we selected a subset of uniprot. So as you know that it has 148 billion triples, but it is too huge to get the experiments. So we took subset from this, like 48 million triples. And get fast, there's no consolidation or no sampling, just get the whole entire dataset into a SHECSA, and SHECSA produce generated one RDF shapes for this 48 million triples. This is a baseline. And we compare the sampling approach and our slicing and consolidation approach. Then we compare the resultant of the shapes for each of them. So this is experimental sets here. So we want to use a very commodity personal computer for doing that experiments. So we just get condition is a memory peak. So this is memory peak rating 0.5 gigabyte or to 6 gigabyte memories. So for each memory setting, we got that kind of this stuff here. So the number of slices for 0.5 gigabyte memory is 77 and 39, 19 or so. And for each slice, it has this kind of number of triples. Okay. Then this is the results we got. So this here is a kind of constraint-based result, and this part is a shape-based result. So this, and also, sorry for it, it's very small, but this part is a consolidation, and also this here is consolidation and consolidation. So our approach, and light bar is sampling approach, and this is also sampling and sampling. So if we compare the result for this consolidation and sampling, the consolidation result will be more reliable and reflect the entire RDF shape baseline. Okay, this is the conclusions. So our prototype outperformed that sampling approach in terms of result quality. And also, even if we experimented with a single source, the approach seemed to be feasible to implement in different scenarios. So we just doing our experiments on the uniprot, but this can be also generalizable to any other RDF datasets. And also future work is study and optimization of the slicing approach, and also the optimization of the shape extraction approach. Okay, yeah, thank you very much.
Thank you for the very nice presentation. And I think it's interesting work in terms of how can we have better performance in there. I was wondering one thing, because in your approach you mentioned about cardinality, right? And if, for example, there is a cardinality of at minimum one or multiple, right?
Yes.
I was wondering, how does that consolidation then happen if the object it refers to is in another slice, right? Does that mean that you're keeping a list of these things and then in the consolidation phase check whether that still is the case, or are you just completely dropping that constraint then?
Do you mean by this one, like at mark here, it's referred to another shape?
Yeah, so if it's at minimum one another shape, right?
Yes.
So because then if you're changing it, then you're basically dropping the constraint.
Yes, yeah.
Okay.
Yes, theoretically, yes, yes. Yeah. So it's kind of some kind of drawbacks here, our approach, yes. Yeah.
Okay, thanks.
I think actually addressing that point, it's possible when you're combining that you're going to throw away some associations. For instance, if you've got an interval start, like you've got repeat start and repeat interval, and those are always associated with each other or something like that, that you might have some groups, like optional groups, where both have to be present or neither is present, but which you could be throwing away in a process like this. On the other hand, you would only want to, you would actually want to be able to do that in the, you would want to be able to isolate that shape, that particular triple pattern in the regular, in the process. How would I describe this? What I'm trying to say is, you've got a constraint that's sort of apparent in your difference between in your A and your B schemas here.
Okay. This one and this one.
But you probably don't want to make it more, the recognition for associations more powerful than you have just in your ability to recognize, for instance, in your A schema. If you find a bunch of data that has interval start, has repeat start and repeat interval, and your algorithm is not powerful enough to notice that they're always associated, then you're only going to be making both of those optional, as opposed to putting parentheses around them and making the group optional. On the other hand, if you up the expressivity to do that, then you won't be able to express it in SHACL. So, but it would be fun to write that, write those write something that would detect those associations. Because I know from, for instance, in Fire, a good fraction of the complexity of the schema comes from those associations, those co-occurrence constraints.
Okay. Thank you for your comment. And Daniel, you have any comments or something to answer? Are you on PC or Zoom now? Okay.
Yeah. Hi. Can you listen to me?
Yeah. Yes.
Yes.
Hi. Well, thank you, all the attendees, and also thank you, Yasunori, for carrying out this presentation. I'm sorry about this last question, but I was not sure about being able to actually speak, so I was answering in typing the previous one, so I missed some of the actual question of this time. But sorry to the previous person making that question. I'd say that maybe when we merge two shapes and there are some constraints that are not the same in these two versions of the shapes, actually we drop. That's true that we drop one of the constraints, but because it's not any longer universal and not working for any observation made in the knowledge graph. But we don't drop totally the constraint, but we only change, we do change the cardinality to 1 too many for a 0 too many. So from the point of view of validation, that is no longer that helpful, because of course whenever you have a constraint there with a cardinality from 0 to many, it will pass. It will always pass. But still, it's I personally think that it is still useful, because you still have in the schema some information that there is a frequent feature there in the instances of that shape that are using this property with this object in this way. Also, as we built this proposal on top of this tool that Yasunori mentioned, ShEx, we are still able to provide to the user some statistics. So if this dropping a constraint occurs because 99% of the version of the shapes still think that there is one occurrence at least, but there is some margin there that thinks that is not happening, the constraint will have a 0 to many cardinality, but at least we'll have a comment there saying, hey, but maybe human moderator, you want to review that, because we found that 99% of the times this is valid if we change this cardinality to 1 too many. I'm not sure if that answers the previous question.
Yeah, he's giving a thumbs up, so yes.
Okay, thank you.
Okay, thank you.
Okay, so let's give another round of applause for the speaker.
Okay, thank you very much.